Hello everyone. Today we will step through the XGSA FD tutorial to evaluate AC interference or AC corrosion on a pipeline in a shared corridor with a transmission line. You can find this tutorial documentation on the help page or start page in the tutorial document links, or going to the help desk on xgslab.com where you can download the CAD files that we will be using for this tutorial. To start, we will create a project in XGSA FD and select project information. This is where we can enter in the name or a general description of our project, as well as customer information, designer, and the site information that can be used to export results and your model to Google Earth. Next, we will set our reference standard, which will be the EN50522, which can be applied for touch and step voltages under fault conditions. And then we will set our frequency, which in this instance we will use 50 Hz. Following the tutorial documentation, we are going to use a simplified uniform soil model. Of course, if you have a more complex soil model and soil resistivity measurements, you'll most likely use the multi-layer modeling or multi-zone soil modeling, which you can learn more about in the tutorial for SRA and seasonal analysis. Following the tutorial documentation, we are going to now import our system. And we can see in our CAD software, we have phase conductors that we will be importing, and this purple line, this VO1 layer, which represents our pipeline. So here in XGSLab, we will navigate to the appropriate CAD file, specify the scale, which will be 1 meter, and then import the appropriate layers. In this instance, we are going to import the EO1 layer, which represents one of our phase conductors. We will specify a line type, and specify tutorial L2. And in the tutorial documentation, we leave the tag name aligned with the layer name, but to give a little more illustration here, we will use phase A. And then I will use the copy feature in order to make this importation process a little faster. So we have the EO2 layer, which will be electrode 2, using the same phase conductor type. We'll have an EO3 layer that we will import, which will be the 3 layer, or the electrode 3. And I'll call this phase C. And then finally, for the transmission line, we will have EO4, which represents the overhead shield wires, which we will represent as an overhead shield wire with a tag name of OH. We also need to import our pipeline that we will evaluate or consider the induced voltages and currents. So that will be coming from our VO1 layer. We will specify this as electrode 5, and we will use a pipe type, specify the pipeline conductor, and I'll give this a pipeline tag name. And note, we do not need to use any shifts in our Z axis because the CAD file that we are importing from already has that information properly considered. Finally, I'm going to import a background layer for the lattice towers to represent those in our model. Importing into XGSLab, it is reading the information from the CAD file and assigning those characteristics based off of what we've assigned in our import table to our virtual model. Here we will see that we now have our CAD model imported into XGSLab. And if we rotate our view, we can see almost identical to what we had seen in our CAD file. Selecting one of our phase conductors, we can also go to the conductor editor and see that the source information or the energization has already been entered. So we have 1,500 amps of steady state current with a 220 kV line to neutral voltage. Following the tutorial documentation, the next stage of our analysis, we need to import or create some longitudinal and transverse impedances. So we'll go to a small section of our pipeline, and we're going to insert a longitudinal impedance. This will be called joint A, and this represents if we had a surge protective device or arresters on our pipeline to help reduce the exposure area. For this, we will use a 650 volt threshold and a 0.001 impedance. Note the symbol is relatively large, so we will reduce that symbol size to a little more illustrative for our visual representation. Next, we are going to put on a joint A right transverse impedance, which will be triggered after 70 volts has been achieved and have an impedance of 10 ohms. And we'll do the same thing on the left-hand side, where we'll put a joint A left with a threshold voltage of 70 volts and a triggered impedance of 10 ohms. Now we'll go to the right side of our pipeline and insert a similar transverse and longitudinal impedance. So select the longitudinal impedance symbol, and we'll put this in as joint B. And then we'll specify the similar 650 volt threshold with a 0.001 impedance for that transverse impedance, or for that longitudinal impedance. And we will now insert a transverse impedance. This will be joint B up. And following the tutorial documentation, we are going to use the 70 volt threshold, but now a 5 ohm impedance once triggered. And we'll do the same thing down below this joint. So specifying 70 volts with a 5 ohms impedance. Now, not all pipelines will have these surge protective devices, but if you do, the software will automatically evaluate your system once you've crossed over that threshold. Once that threshold has been crossed, we will have a continuous pipeline, and we want to make sure to avoid end effects. To do this, you can easily insert an infinite section onto the end of each of our edges of our pipeline. And this will allow us to avoid any end effects in our modeling analysis. Now we will go to the debug and compute. At this stage, the software will evaluate that all conductors are independent or they're not overlapping, and evaluate the inductive coupling, conductive coupling, and capacitive coupling that may occur from your transmission line to your pipeline or other metallic structures. Once completed, we can see in the Analysis tab that none of our surge protective devices had been triggered, and we can look at our results by specifying, let's say, potential, and we just want to look at the pipeline potential, and we can look at this as a 3D view, and we can see a significant voltage at that transverse or longitudinal impedance here. We can also look at this as a 1D view. And note that I have selected the modulus, real, and imaginary components so that we can get all three of these lines visualized, as well as the symbols so we can see where our joints are located on this plot. We can look at the leakage current of this, and a leakage current that would make go through a small holiday. So this can give us our amps per meter squared to evaluate possible AC corrosion during steady state conditions. The next portion of this tutorial is looking into fault conditions. As we've looked in so far, we've just evaluated steady state conditions for a transmission line next to a pipeline, which will evaluate the pipeline voltages for personnel safety aspects, as well as the current through any holiday or holes to evaluate AC corrosion. To facilitate the AC interference under fault conditions, we're going to import our next model. So we can go to the import icon here. Actually, before we do that, let's go ahead and delete all of our transmission lines from our model. And this will speed up our process because we do not need to re-enter our information regarding our pipelines. So I'll go to the import section again. I'm going to deselect my pipeline for the importation. I will go to the directory where my fault CAD file reference is located. And I will select the append option and import. This way I can import the transmission line once again from our faulted condition that's provided in our help desk without having to re-enter the transverse and longitudinal impedances. Of course, you can follow the steps in the tutorial documentation to re-import that as well. So now we can see if I select one of my phase conductors that our current is dramatically increased into 14 kA from the 1500. So this represents a fault condition, and we are going to hit the debug and compute. Now the system will take longer to process. Note that these errors are indicating that some components will, based off of the forced source currents, not be respecting Kirchhoff's current laws. This is an expected warning from our template. Now, the analysis will take a little longer because when we are using these more significant fault current on our phase conductor, that is inducing a higher voltage on our pipeline. And because of that higher voltage, we are going to exceed the voltage threshold of our surge protective devices. Thus, the surge protective devices will operate on the left and right side of our pipeline. And then the software will automatically consider that and run the analysis again, considering these changes. And just a few more seconds and this analysis will be completed, and we can take a look at the induced voltages and current on our pipeline. Now that operation is completed, we can take a look at our results. First, we can see in our surge protective device table that all of our transverse and longitudinal impedances have triggered, indicating that we've exceeded those threshold voltages prior to their triggering. Now that they've operated, these impedances will now be considered in the analysis. So we can take a look at the results of this by going to our potential tab. We'll select just the pipeline tag and visualize the pipeline voltage. And we can see a continuity as the voltages on those surge protected devices has been triggered, allowing continuity from one portion or the right side of our pipeline to the left side. We can also see this illustrated in our current. And for fault conditions, we want to evaluate the pipeline's coding stress or covering stress voltage, which we can do by selecting the covering stress voltage dropdown and plotting either in 1D or in 3 dimensions to illustrate the significant voltage that's induced upon this pipeline.